Good afternoon, everyone. Happy to be here. Thanks for the organizer for the opportunity for me to present here. So today I'm going to talk about quantum machine learning, and to be more precise, quantum convolutional neural network on a photonic device. And I'll show you how to apply that to malware classification, a use case brought to us by our client, Orange. So this is a work done by mostly Quandela team from the algorithm side. So here you have few names like Daphne Wang, Pierre-Emmanuel Emerio. And on the Orange side, so the use case was brought by the R&D team from Tony Cartier and Grégory Barvet. And as I was saying, I'm going to first introduce what convolutional neural networks are about, so the basic principle of it, fully classical. And then we're going to shift to how we develop a photonic native quantum circular convolutional neural network, and then apply it to actual use cases as the MNIST dataset and malware classification. So convolutional neural nets, they take their inspiration from how the brain is actually working. So these are discoveries from the 60s from Hubble and Weisel, where they realize that the brain is working in like a hierarchical structure. First, it highlights, it notifies the different line of an image, and then it focuses on a specific part of the image to have more details about this specific part. And then it repeats the process over and over. There's also a key part, which is position independence, meaning however you translate the image, it remains the same image. And this can be shown with this little cat. If this little cat is like up high in the air or close to the grass, it's actually the same cat that you want to recognize. And so this is how a typical convolutional neural network architecture is. So you first start with a convolutional layer, which is a translation-independent operation that you have on your image. And then that enables you to sort of analyze the different traits, the rough traits of the image. And then you focus on a specific area. This is the pooling layer. And then you repeat this process as much as you need. And you end up flattening the image and having a dense layer doing the end of the classification. And to focus a bit more on how it works, so first, on the left, you see our image. So it's grayscale pixel images. And we're going to apply the convolutional operation on this one. So we take a kernel. That's how we name it. It's a 3x3 image as well, but these are parameters that you're going to train in order to optimize the performance of your model. And then you essentially do a dot product. So you take this kernel and multiply it on each pixel of your image, and that's how you're going to reproduce the coming image. So you do that for the first part on the top left, and then you repeat this operation over and over on each part of the image, and you reconstruct a new one. And that's how you do your convolutional operation, which is translation invariant. Then you have your pooling layer. So this one is about taking the average or the max of a bunch of pixels on your image. So for instance, we take the first 4 on the top left, and we're going to do the average. So that's going to give us a new pixel. And then we repeat that again on each part of the image. And we have this smaller image that is taking the essence of the previous one, but in a smaller dimension in a sense. After that, we're going to flatten the image, so make it a 1D vector instead of a 2D matrix, and feed it to a dense layer, a classical dense layer. And this is going to tell us the result about whether this image belongs to one class or the other. Then I'm going to explain to you how you can make that quantum. And to be more specific, we have the circular component, and at Quandela, we do photonic quantum computing. So I'm going to explain how we develop a photonic quantum circular convolutional neural network. So first, our work is related to these two. On the left, you have the subspace preserving quantum convolutional neural network architecture, which tells you that if you manage to preserve the number of particles in your system, in our case it will be photons, but it can be different particles, you avoid some barren plateaus, meaning it will be much easier to train your model. On the right, it's a proposal for a photonic architecture using state injection. So I will explain what this means afterwards. And we based on this work, and we add this circulant component in order to make and to have better results. So first, the convolutional layer can be as follows. So it has to be. So let's say that in Photonic we can make it a circulant matrix, and which makes it more adapted to what we have, because we need like periodic boundary condition, and it's really important for that to have a circulant matrix. And then the pooling layer will be as follows. So what I just showed, was the convolutional layer. What you have here is the pooling layer. So the pooling layer will be what we call a feed-forward operation or adaptative measurement. So for instance, if we look at the top left 4 pixels, it will be represented by optical modes on the photonic quantum processes. So the first 2 modes, so the P modes you see on top and the P modes you see on the bottom. And what we're going to do is just measure whether we detect a photon or not in those modes. And depending on that, we're going to either inject a photon in the rest of the circuit or not. So that enables us to preserve the number of particles, because if we measure a photon, we send a photon again. If not, we don't send the photon, as shown on this slide. And that's equivalent to an adaptive measurement. So depending on whether you measure or not a photon, you will send another photon in the circuit. And you do that for each pair of modes, meaning for each part of the circuit, of the image, sorry. And what's really important in this one is that we do, it uses adaptative measurements. And adaptative measurements make the computation much more complex for a classical computer to simulate. And as I was saying, we do that for each pair of modes. So if you want to do it for your full image, that's how your circuit will look on the left, a photonic circuit. But I didn't tell you that. But we have 1 photon in the first N1 modes and 1 photon in the following N2 modes, which means that in the end it's equivalent to just doing the adaptative measurement, or to re-inject a photon in one of the modes, so just the first one of each group of modes. And this is how you end up with your much smaller image, which takes the essence of the original image. And the last part, so as you saw before, we had a classical dense layer. In this case, we can also have a quantum dense layer, which is just like a generic interferometer, where we have parameters that we can train. And at the output of this, we have a lot. The probability distribution is quite big. It's 2 amongst m plus 1, with m the number of modes. So in this case, m is n1 plus n2. But we maybe want just n. We just have n classes. So what we want to do is to reduce the space we're in by simply like a dense layer. So that's a classical dense layer we had at the end of the process. And here you have the full process. So we start with our N1 plus N2 modes, which represent the dimension of the original image, on which we have, then we prepare the state we want. So this we assume we know how to do. And afterwards we have a repetition of the convolutional layer, which is the circulant matrix, which we introduced in this work. And after that, we add the pooling layer, which is done by this feed-forward measurement or adaptative measurement, where you can see that's where we detect the photon in this part. And we're going to repeat that as much as we need to analyze our image. And in the end, we have this quantum dense layer, which is then followed by a classical dense layer. And now we applied it to malware classification, which is a use case we developed, we analyzed with Orange. But before jumping onto this one, we actually have results on the MNIST dataset, which is like maybe the first basic thing you want to try your convolutional neural network on. So as a reminder, the MNIST dataset is about digit recognition. So you have image of zeros, 1, 2, 3, and you have 10 different classes, and you want to well say, oh, that's a 0, I recognize it as a 0. That's a 1, I recognize it as a 1, and so on. And so we did it with our neural net, and we had pretty good results. So as you can see on this image, so that's you have the confusion matrix of it, and you see that we mostly, so that's the more accurate result. We have above 90% accuracy for our model on the MNIST dataset. And what's really interesting is that, well, with the similar amount of parameters, we trained a convolutional neural net, and we see that the training is not as good. So it plateaus to like 75%. Whereas our model, the quantum circ convolutional neural network, reached 91%. And same for the photonic quantum CNN from the related work I presented before. Even more interestingly, we see that if we aim for a given accuracy, and we add noise to the image we try to classify. So that's what you see on the x-axis. The difficulty of the task is just adding noise to the images. On the y-axis, you have the number of parameters in the model. And for a given accuracy, you see that with the quantum model, you need much less parameters to reach a certain accuracy, as the complexity of the task increases compared to the classical one. We see that there's a big gap as we increase the complexity of the task in the number of parameters needed. We need much less quantum parameters compared to the classical model. And so that's kind of, well, it can be related to some use case, but it's kind of like standard benchmark and pretty artificial. What we are doing now, and that's still work in progress, I'm just going to show preliminary results today, is applying this algorithm to the classification of malware. So malware is a malicious software that one wants to detect in cybersecurity. It can be represented as a binary file, so a stream of 0 and 1s. And what one wants to do is either detect whether it's a malware or not. What we can do with those malwares is actually represent them as images. So what you can see in the second step is an image representation of a malware. And you can either try to classify it as a wall. So say you have this image, you feed it to the convolutional neural net, and you directly try to ask it whether it's a malware or not. Or, and since the quantum computers today are relatively small, we can try to cut it in different parts. So have section of the malware and then feed each section to a different convolutional neural network. So that's an idea by Orange that we brought into this work. And once you have fed each section to a different convolutional neural net that you have trained on the different section, you just recombine the different convolutional neural net using like boosting method or random forest. And if you have, for instance, 0.89, which is about 0.5, then you declare that's a malware, and you were able to spot one. And the result so the result Orange had before, so using Qiskit from IBM on the war image, no segmentation, straight on the first image of the malware. It's 60% in accuracy on IBM machine and 66% for the F1 score. With the approach we developed at Quandela with the photonic quantum circular neural net, convolutional neural net, we managed to have 70% of accuracy and 70% of F1 score using the image as a whole. What we target now is the score they managed to have on IBM devices, segmenting the image. So it's 82% as accuracy and 80% as FN score, whereas we see they're still far away from the classical benchmark. We believe, based on the results we had previously on the wall image, that we can reach maybe 90%, so outperform the IBM solution and maybe be a bit below the classical state of the art. But what we hope is that even it's a bit lower accuracy, we use much less parameters, which make the model much more resource efficient. So as a conclusion, we developed a quantum circular convolutional neural network based on circulant matrices. So this model is quite elementary. It can be implemented with basic single photon source that we have at Quandela, reconfigurable Mach-Zehnder interferometers, simple adaptative measurements that is being actually now tested in the lab. And what we saw is that our model outperforms similar classical models while needing much less trainable parameters. And that applying it to real cases gives good enough result, but we believe it can be more resource efficient for an actual cases like malware classification. Thanks for listening.
Thanks, Arno. That was a really crisp presentation. We have a question from the audience. So someone is asking, what difficulty of task numbers mean that you described?
OK, thanks for the question. So what we mean in the difficulty of the task is, so the no difficulty task means having an image that is really clear, no noise, really easy to read with human eye or for a machine. And increasing the difficulty task for us meant adding noise, so Gaussian noise, to make the image harder to be read by a machine or by a human being. And as we increase, so increasing the difficulty of the task just meant increasing the Gaussian noise we were adding to this image.
Thank you. And if I may ask a question myself, was there any error mitigation techniques that you applied or that was suitable to the kind of hardware? Because I know that you developed the hardware as well.
That's a good point. No, for now, we haven't tried any error mitigation technique. Everything was done using perfect simulation, meaning strong simulation. So we have the full probability distribution. So we did not need, for now, to have any error mitigation technique. But as we go forward, we'd like to implement that on QPU. And there's still a few things, specifically in the state encoding, that we need to tackle before before running it on the actual QPU. And once we'll have to run it on the QPU, then we'll need to add error mitigation technique to make sure that the noise does not impeach us to have good results.
Exactly. OK, that's all. Let's thank the speaker again.
Thank you very much.